Okay, today we're going to be talking about some two-sample tests and intervals. This is section 11.2. We have done t-tests and t-intervals for one sample, and now we're going to talk about two separate samples. The purpose here is to compare the means. We're still testing um, for means, but we are going to compare the two. These are some grades out of 26 for test multiple choice. They're not in any particular order, they're mixed up. But these are what my A2 and my A3 classes got on their multiple choice portions of our last test. So what we're going to do is see if these are statistically different or the same, and then get a confidence interval for that difference. Let's start with the conditions. Um, these conditions are going to be similar to the conditions that we did last time. As always, we need to assume that we have two SRSs. It's usually been one SRS, but now we're going to have two. These need to be simple random samples. In this particular example, I wanted to use real data, so this is not really a simple random sample of anything, but you could, in most cases, it'll be simple random sample. So we're going to kind of fudge that rule a little bit with this one. The samples need to be independent also. All right, one sample shouldn't have anything to do with the other one. And matching up, like a match pairs like we did last time, that is not going to be a two-sample t-test. That's a one sample that we've already covered. And as usual, both populations are either normal or the sample is big enough to normal it out. Okay, we can deal with non-normal distributions as long as we're looking at a big enough sample so that the sampling distribution would be normal. And some of the questions they'll ask you to kind of check to see if it's normal, and you can do that by making a graph or just doing old ways to check normalness. And usually you just assume it is and say if it's not perfect, well, it's good enough. Okay, so let's start with our test. Let's do our two-sample t-test by hand, and then we will do it by calculator. Okay, so let's start by hand. Remember what this is for. This is to check and see how the means are related. Okay, your hypotheses for a two-sample t-test. Your null is that there is no difference, or the average of one is equal to the average of the other. And your alternative is that they are either not equal or one-sided or the other, that mu1 is bigger or mu1 is smaller. Now I'm going to consider my A2 class to be population 1 and A3 to be population 2. And just by glancing, it seems like there's not very many numbers in the 20s anywhere, but it seems like there's more high teens in the sample 2. So I'm going to hypothesize that mu1 is less than mu2. So we are always going to undergo 4 steps. Step 1 is the hypotheses, so we have those laid out. Step 2 is to check the conditions. I said before, these aren't really simple random samples, but we're just going to kind of fudge on that one. And we have decent sized samples, so we're kind of fudging on that one too. You could graph them and show that they're not really skewed or not really crazy. So forgive me, but we're going to kind of pass over the conditions, even though we shouldn't. At least, if you're doing your 4 steps and the conditions aren't met, you kind of can write out, we're going to assume that this is simple random and that it's normal enough. You're going to kind of pass that over. Okay, so next, we need a formula for calculating t. This is a good one. T equals, here we go, x1 bar minus x2 bar minus mu1 minus mu2 over square root of s1 squared over n1 plus s2 squared over n2. notice there's a 1 and a 2 for each one. Um, there are means and standard deviations and sample sizes for each of my two populations.
The thing about this formula is your hypothesis is that mu1 equals mu2. That's what's assumed to be true. So if that's true, then mu1 minus mu2 is 0. And all of this part over here is pretty much going to be gone out of your formula when you're doing your calculating. Okay, so let's see what we need to know. You need to know some things about each one. You need to know the sample standard deviation, you need to know the sample size, and you need to know the sample mean for each one of these two sets. Now, those are easily found in your calculator, so I've pre-entered them into my calculator in list 1 and list 2. And what I want to do is go to Stat, get rid of that highlighter. I want to go to Stat, I want to go to Calc, and do two variable stats. I have two variables typed in, and this will give me, just a moment. Okay, sorry about that. I'm not sure what happened with my calculator. It won't do two variable stats, so I'm just going to do them one at a time. Shouldn't be any problem. Okay, so one variable stats tells me that for, let's see, this is for my A2, which is my first population. My average was 14 points, let's call that 087. Then I need my sample standard deviation and my sample size. My standard deviation is 3.579, and my sample size is 23. Okay, so then let me go back and do stat, calc, one variable stats on list 2. And here's the info for list 2. I have an average of 17.529. And I have a standard deviation of 2.267. And I have a sample size of 17. Now, at this point, it kind of seems like, why are we doing a test? If I'm testing to see if one class is better than the other, or did better than the other, I know that my A3 did better because they averaged 17.5, while A2 averaged 14. But the point isn't, is their average better? The point is it statistically significant? Did, you know, if these two classes were exactly paired up evenly, and they had the exact same strengths, if you gave them the same test on the same day, then one class, you know, they don't have to get the exact same thing. So what we're testing to see is this approximate 3.5 point difference, is that significant, or would that just happen by chance if they were really, you know, equally matched? So let's plug these numbers in and see what our t-value is. Okay, t equals, we have x1 bar minus x2 bar, so that's going to be 14.087 minus 17.529. Remember, the other part is washed out because we are assuming that they're the same, so mu1 minus mu2 would be 0. Over s1 squared, so that's going to be the 3.579 squared, over the sample size, 23, plus the second standard deviation, which is 2.267 squared, over the 17. So all this is going to go together to give us a t-value, which will tell us, did this difference just happen by chance, or is it because the second block was more prepared for whatever reason? I'm going to pause and do some calculating and then be right back. Okay, I'm back. So you can see I like to do this in steps as you go through the calculator. I did the bottom portion under the square root. I did that all together. I did the 3.579 squared over 23 and the 2.267 squared over 17. I entered that, then I square rooted that whole thing, and now I'm going to do the top divided by that bottom. Just kind of go through a step at a time, and we get a t-value of negative 3.71. That'll be good enough, negative 3.71. Okay, so t's are not exactly z's, but you should recognize that 3.7 is a pretty extreme t-value, even if we're not using the same old z's. 3 is a big, 3 or negative 3, those are big z-scores, so this should be a pretty big t-value. So let's look up and see what's the probability that this would happen, assuming the classes were the same. So what we need is to look at our chart, which is here, and I've got some old ink on there I need to get rid of. And we need to figure out what's the probability that this would happen, assuming the classes were same prepared. Now, the question you need to know is what line to go to. There are two solutions to that problem. There's a difficult solution with a big crazy formula to find the degrees of freedom, and that's the one that your calculator will use because it's a lot faster than you. But the one we're going to use is just use the smaller of the two. My smaller sample had 17 numbers in it, so I'm going to use 16 degrees of freedom just to play it safe. So we're going to go to line 16 and look up 3.71. It doesn't matter if it's positive or negative because of the symmetry of the thing. So we can go to line 16, looking for 3.71. And let's see, line 16 is here, looking for 3.71. And it is on the charts, and we're somewhere between 0.001 and 0.0005. So that's somewhere between a 0.1% and a 0.20%. 0.001 and 0.005. So we have a very small p-value. So our conclusion would be we reject the null. All right, at any level, at 5% or 1% level, we're going to reject the null that says that the classes were going to be the same. We knew that the second one was higher, but a difference like this wouldn't just happen by chance. So for some other reason, A3 did better other than just chance. So we reject the null. We conclude, or let me start over and say there is strong evidence that mu1 is less than mu2. And I should use context there and say that the average for A2 is less than the average for A3. And that doesn't mean anything because I just wanted to use some real numbers, but these weren't simple random samples, and this doesn't mean anything, real world wise. So the only reason I used this was to do some context that applied to our classes and to get experience with the formula. Now, to quickly do this with a calculator, we're doing stat test. We are doing a two-sample t-test. All right, now I want to input data. That's really easy. You don't have to know anything about it except what the numbers are. And list 1 is list 1 and list 2 is list 2. And what we are checking to see is whether or not, wait a second, stat test, two-sample t-test. We are checking to see whether or not mu1 is less than mu2. You can leave pooled at no for now and calculate. And there's our t, negative 3.71. There's our p-value, 0.0003. And, it gave us the degrees of freedom to 37. That's the complicated way to figure it out. It'll also give you the means and the standard deviations and the numbers and all that that we learned before. So doing this strictly in the calculator is a piece of cake and should go very easily. All right, so that's, we didn't get to intervals, but this video is getting too long, so we're going to leave that as two-sample t-test, and we'll talk about the intervals later. It's just a different button in your calculator. So, this is Young. I'm out. Have a significant day.